Okay, let's finish up this chapter 15. I wanted to start back on this slide. There's a couple of things I'd like to add. First of all, let me point out in the frequency and period down here on the bottom right. Notice the variables that are involved. Both of them have K and M. K and M are both physical parameters in the system. The K is about the spring itself, how strong the spring is. The mass is how much mass is attached. Notice those are parts of the system. I set those up at the start. I choose a spring, I choose a mass, and that determines how the oscillations are going to work in the system, how much the period is going to be, how quickly it's going to oscillate. It doesn't matter how far I pull the system back, what amplitude I set in the system. It's going to be the same no matter what. So you might say that a given system has a natural frequency based on K and M. A given system has a natural frequency based on the spring that you choose and the mass that you choose. It's going to oscillate at a certain frequency. Also, I wanted to take these equations and specifically focus on the first one. The others are going to be exactly the same, and say that there is a more general version of these equations. So more general. And in this particular case, what would happen if we shift things a little bit? So let's say, what if at the starting time, we're going to say that theta is not equal to 0. In other words, let's go back to this slide. Notice in this particular case, we're starting the curve at maximum positive amplitude at t equals 0. What if, on the other hand, what if we did something like this? What if my vertical axis was here? What if this was t equals 0? I still have the exact same curve, but it's offset by a little bit. This offset is what we call phi, which is our phase angle. So let's say the offset is phi, the phase angle. Now in this particular case, how much are we off? You can see that looking at my curve, this is 1/4 of a complete curve. 1/4 of a complete iteration of the curve. One repetition is the same as saying 1/4 of one rotation. If you said one rotation was 2 pi or 360 degrees, then this is 90 degrees or pi over 2 out of phase. So in the previous example, so on the previous slide, phi or phi is pi over 2. So we could write the position equation. X as a function of t in general is going to be a cosine omega t plus phi, which will handle all the offsets, and we could have a phase angle in our velocity and acceleration equations as well. So this is the more general equation that happens, that takes care of all those possibilities. So let's see, we did those slides, which brings us to energy considerations. Energy considerations. So if, again, let's imagine we have something in simple harmonic motion, and specifically we're looking at simple harmonic motion for a spring mass system. We could say that the total energy at any one point is, of course, equal to the kinetic energy plus the potential energy. And if we're dealing with a horizontal system, then we could say this is 1/2 mv squared, and the potential energy is all coming from the spring and the amount of stretch or compression that's in the spring. So, if we have a spring that is fully stretched or compressed, and by fully we mean it matches whatever it started at. It's not like the maximum amount you can stretch it or the maximum amount you can compress it, but we'll say the starting stretch or compression. In other words, it's at its amplitude. It's as far as it's ever going to go in either direction. In that particular case, we would have all potential energy, which means that the velocity at those points are zero. It is turning around. And we could say that the total energy is 1/2 kx squared. But the x in that particular case is the amplitude. If you take a look at the graph over on the right, we have a potential energy graph. Notice it's oscillating between negative A and positive A. At these turning points, the places where it stops and turns around, all of my energy is potential. We're all the way up at the top. Okay. On the other hand, if we have no stretch or compression, let's say we're at the equilibrium position. And in that particular case, x is equal to 0, and we have all kinetic energy. Nothing is being stored in the spring. In this particular case, we have our velocity at a maximum. So we could say that the total energy in this case is 1/2 mv squared, but that velocity is the maximum velocity, and that would correspond to the case right here in the middle. And you can see that it's all kinetic energy, but my potential energy curve has gone all the way to 0. So if I were to compare what these two things are doing as it oscillates, and we're assuming no energy losses here, so assuming the work done by non-conservative forces is equal to 0, no energy losses, you just have an oscillation between the two. If I start at the amplitude, at the maximum stretch or compression, I'm all potential energy and no kinetic energy. And then as we oscillate, well, the potential energy begins to drop, and at the exact same time, kinetic energy begins to go up. And eventually those will cross, and we will switch to where I have all kinetic energy and no potential energy. At this particular point, we are at the equilibrium position. And then they go back the other way once again. So we could say here we are at plus or minus A. It could be either one because they're just looking at magnitudes. And then over here, we're at plus or minus A. And this is at x equals 0. Okay, so it's just oscillating between the two types. We're going to see how at least the potential energy curve changes a little bit later on from this. So let's look at a quick example. In this particular case, we have the mass that you can see at the bottom attached to a spring. It's currently at position x1, moving with velocity v1 to the left. We're going to say that that is my initial position. Now keep in mind, if it's at that position and moving, that must mean that there's some other position over here somewhere, which is the maximum position. So it started at some position farther to the right, and now it's moving to the left. So we're going to find a few different things. First of all, let's set this current position as the initial location, and then we're going to let the final position be at the equilibrium position right in the middle. So using those two, let's use conservation of energy. So KE initial plus PE initial, and I have both of those at the initial position is equal to KE final plus PE final. And WNC is going to be 0. For all these cases, we're assuming no friction for all of this. So at the initial position, I do have 1/2 mv initial squared plus 1/2 kx initial squared. And there is no potential energy at the equilibrium position, so I just have 1/2 mv final squared. And that v final is going to be the maximum velocity, which is something that we can find. So let's see, the halves cancel out, and you can rearrange things there and solve for the final velocity. And let's see what happens. We're going to have to divide everything by mass and take a square root. So that's going to be v initial squared plus k x initial squared over m, and take a square root. So we have the mass. They gave us that as 750 grams or 0.75 kilograms. We know v initial and x initial. They gave us both of those, which you can see down here. The one thing we don't have is k. However, we've got enough information to find that really quick. So keep in mind that omega is equal to 2 pi over the period, and that's also equal to the square root of k over m. They gave me the period, and they gave me the mass, so I can solve that for k. So let's see, that's 4 pi squared over t squared is equal to k over m. And then we could rearrange that and say that k is 4 pi squared m over t squared. And you should get 94.32 newtons per meter for k. And once we have that, life is a little bit better, and we can plug that back in for k and solve for the final velocity, which is v max. And for that, I have 0.6 meters per second. So once we have the final velocity, we could also find the amplitude, the maximum stretch or compression. So to do that, let me change colors, and we can do this a few different ways. Let's imagine that the mass continues to go over to the left and ends up over here somewhere. And let's now set that to be final and here in the middle to be initial. So now we're going to let the final be at max compression. And we can use conservation of energy once again. KE initial plus PE initial equals KE final plus PE final. And we're going to say at the initial position there's no stretch or compression, and at the final position there's no kinetic energy because it stopped moving. So I have 1/2 mv initial squared, and we'll use our v from before, and that's equal to 1/2 kx final squared, and we can solve that for x final. So let's see, this 0.6 is going to go right there. We know what k is, so you can find x final. And let's see, I've got that number here somewhere. Where is it? Looks like 0.054 meters. So I can do one additional thing with this. What if I wanted to write the equation that describes this motion? In other words, I want to write x of t is equal to x max, or the amplitude. Let's write that as amplitude instead. So this is equal to a. Let's write this as a cosine of omega t. Omega is equal to the square root of k over m, and I have those numbers, so that gives me 11.2. So this is going to be 0.054 times the cosine of 11.2 t. That describes the position of the end of the spring, or right at the edge of the mass, at all possible times t, using conservation of energy. All right. So let's see. I have a blank slide there that we don't really need for any particular reason. What do we have here? A mass oscillates in simple harmonic motion with amplitude a. If the mass is doubled, but the amplitude is not changed, what will happen to the total energy of the system? Well, the total energy of the system can be defined either in the all kinetic energy state or all potential energy state, or at some point in the middle. But here we're talking specifically about whatever happens to the amplitude. So it's equal to 1/2 k a squared. Notice the mass has nothing to do with this. K is going to have something to do with how much energy gets stored based on a given amplitude. In other words, how much work I do to initially stretch or compress the spring. But if I don't change the amplitude, it doesn't really matter. The total energy is not going to change in the system. So there we have the answer for that. One other example we have for simple harmonic motion is the simple pendulum. And this is going to work as long as I have small oscillations. show you why here in just a second. So in a simple pendulum, we have something that looks something like this. Maybe we've got a string, the mass on the end, and perhaps you could imagine that somewhere right at the bottom, as this swings downward, this is the equilibrium position. And it's going to oscillate around that point. So it would swing down and swing up to the other side and so forth. Okay? So let's take a look at the forces on that mass at the place where we've drawn it. So we're going to have a tension force this way, and we will have a gravitational force straight down, which we'll describe as mg. And then something needs to make the mass swing back to the left. So I need motion in this direction. Well, what's going to cause the motion in that direction? It's going to not be the tension force because it's perpendicular to it. It's not going to be this component of the gravitational force. There's theta. But it's this component at the bottom, mg sine theta, which is what is making it go in the general direction of the equilibrium position. Now, of course, that's traveling along an arc, which means it's not pointing exactly to the equilibrium position, but it's pointing along the arc or tangent to the circular motion along which it's moving. So you can start to see where we're starting to make some approximations, and as long as it's not too large of an angle, well, then it is pointing back toward the equilibrium position. So this mg sine theta is what might be the restoring force in this problem. It's the force that's driving it back toward equilibrium. So let's go up to the top here and take a look at this. So my force is equal to mg sine theta, and theta is the displacement. Notice the force is not directly proportional to the displacement. F is not directly proportional to displacement here. Which means it doesn't satisfy the requirement for simple harmonic motion. But as long as I keep the angle small, the displacement small, the oscillations relatively small, it does work out. So we can say that sine of theta is roughly equal to theta for small theta. This is known as the small angle approximation. And if you want to just test it on your calculator or just graph theta and sine of theta and see where they diverge. They're typically about the exact same number as long as we're less than about 22.5 degrees. Anything greater than that and they begin to diverge, and this is not a good approximation anymore. So we can say that F is approximately equal to mg theta. And now, notice we do have a directly proportional relationship between F and theta. So things are a little bit better here. But let's take this a little bit farther. Remember our arc length equation. So the arc length is equal to r times theta. And in this particular case, r is the same as the length of the string, or the length of the pendulum. So I can say that theta is equal to s over L, and then plug that back in, and now I've got F is approximately equal to mg s over L. mg s over L. So in this particular case, mg over L is a constant, and s is the displacement. It's how much arc length I've pulled the mass backwards along. Okay? So mg over L is analogous to K, the spring constant from before. Which means we could just take our equations from before. Remember that omega is equal to the square root of K over M. Well, what if we just plug mg over L in for K? Then I'm going to get the square root of mg over Lm. The m's are going to cancel, and now omega is equal to the square root of g over L. And if you wanted to continue with those substitutions, you would find that the period is now equal to 2 pi square root of L over G, and the frequency is 1 over 2 pi square root of G over L. And you'll notice, once again, has nothing to do with the amplitude. In this case, it even has nothing to do with the mass. It's all about the length of the pendulum, the physical characteristic of the pendulum that matters and drives how fast the oscillations are going to be is all about the length of the pendulum itself, which is kind of interesting. And we could also write an equation if we wanted to that is theta as a function of time is equal to theta max, which is my amplitude in this case, times the cosine of omega t plus phi would be my general equation of motion. So we have a similar problem here using conservation of energy once again, where we are given, oh, actually this one, nope, we're not doing that one. This is the one, where is the one I wanted to do? Oh, it's a little bit later on. Let's see, so first of all, answering this question, how do the periods compare if I have two pendula that are the same length but have different masses? We'll go back and look to the equations we were just talking about. The period is going to be the same in both cases because they have the same length. So here I have a pendulum of a given length that's pulled aside and released from rest at t equals 0. The fact that it's at its amplitude, at its maximum displace at t equals 0, means that the phase angle is 0. It's not out of phase. It's at maximum displacement at the starting time. And then it says at some time the pendulum string is found to make an angle of 27 degrees when it's moving at a given speed. So it's not at the maximum displacement when we're given this information. So this problem really sets up just like the spring mass system problem that we had before. So let's see. Let me draw a quick diagram. Let's say that we have the length of the string here. We've got our mass here at the bottom. It's going to go swing down here to some bottom point, which we'll call the final position. Just keep in mind, it must have started at some higher position, which they didn't tell us about. So this is initial, and that's final for the first case. So we could say that kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final minus WNC, and we're going to say that there's no work done by friction in this case, or air resistance for that matter. It's at the bottom when I have no potential energy and it's moving the fastest. So there is enough information there to say 1/2 mv initial squared plus mgy initial equals 1/2 mv final. The m's cancel out, final squared that is. The only weird thing in there is, well, y initial. So keep in mind, you have to be a little bit careful. Maybe we're saying that this is y equals 0. You need to find what that height is. That is y initial. And there is enough information there, if you know that this is 27 degrees, to find how much height you have at that particular location. It turns out it's going to be, let's see, the length of the string minus the length of the string times cosine of 27. So let's see how to draw this in. This length is going to be L cosine 27. And this length, all the way down to the bottom, is going to be L. So that means y initial is L minus L cosine 27. We subtract the pinkish purplish line from the green line, and that's going to give me y initial. So you should be able to solve that for v final, which is the maximum velocity, and get 1.68 meters per second. Let me warn you, in this problem, keep a lot of digits. It turns out that the numbers that were chosen are really, really close, such that if you don't keep a lot of digits, you're not even going to see that the starting angle is something bigger than 27 degrees. It's barely bigger than 27 degrees. So you have to keep a lot of digits throughout the problem just to be on the safe side. So once you have that, we could imagine this thing swinging past the final position and then up to a maximum position on the other side. So let me draw this once again. Let's go back to red. And let's say that all the way at the bottom is my initial position. And now it's going to swing up to some higher position. That doesn't look great, but it'll work. So this is y equals 0. Up here is going to be y final. We're going to say that that is final and initial is at the bottom. And we can once again say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. And we're going to have no potential energy at the bottom. The potential energy here is just coming from gravity. And then we're going to have no kinetic energy at the top. So 1/2 mv initial squared, where v initial goes there, is equal to mgy final. The masses cancel out, and then you can find this y final. And for that y final, I've got 0.1435 meters, which can be used in reverse to find theta final. And you should get 27.2 degrees. Again, keep a lot of digits to work that out, but you're essentially using this process over on the left again to work backwards to use that y final to find that corresponding theta final. So a couple of other things that we can do. We could say that omega is equal to the square root of g over L for this, and you're going to get 2.75 in that particular case. So I can write the overall function for theta as a function of time, and that's going to give me 27.2 degrees times the cosine of 2.75 times t. And there is no phi because, again, we said it's 0 all the way back at the start. So there is that problem, which just leaves me with a couple of things in this chapter that I'd like to talk about a little more theoretically. For everything that's left here, we're not going to do any math. Don't worry about math for these last two sections. I just want to point out what's happening in this case. The first one is damped oscillations, which is what happens in the real world. These oscillations can't continue forever. I pull a pendulum aside and let it go. We've made the assumption it's just going to go back and forth at the exact same amplitude forever and ever and ever and ever and ever. We've made the same assumption with the spring. You pull it back, it goes back and forth to the same amplitude, positive and negative, forever and ever and ever and ever. In the real world, we're going to have an oscillation that decreases, and it decreases exponentially in amplitude over time and will eventually stop because there is lost energy, quote, lost energy, due to friction or some other non-conservative force that's taking some of my energy away. So a more real-world way to sort of represent x as a function of time might be something that looks like this. Yes, still a cosine curve, but instead of making it all the way back to the amplitude, you can imagine it looks something like that. With each oscillation, it loses a little bit. Now, that may happen quickly. It may not happen quickly, but you can see there's sort of an envelope here. It's a little hard to draw, that shows that the amplitude is decreasing exponentially over time. So mathematically, we could work through all of that. We're not going to do that in this class. I just want to point out that there's some different types of damping. First of all, what I've drawn above is what might be called underdamped. Underdamped means that there's not a lot of resistance to the oscillations, which means that there are oscillations that die out. But it may take a little while, it may not, but it goes through at least one full oscillation because it hasn't been damped enough to stop them right away. So there's oscillations that die out like you see above. There's also critically damped. In this particular case, there are no oscillations. Instead, it just returns to equilibrium without overshooting. So you might imagine in this case, if I look at x versus t, I pull the object back in an oscillating system, I let it go, and it begins to go back towards zero, but then it just settles on zero. It never overshoots to start working in the opposite direction. It just quits right there. No oscillation at all. It returns to equilibrium without overshooting. In other words, without going past the equilibrium position. And then for overdamped, what we should say that there's also no oscillations, but we'll say it may not return to equilibrium. That shouldn't be there. So in this particular case, we have a situation where I pull the object back. I started at some amplitude, but now maybe it just sort of stops there. In other words, I have a spring or a mass that has so much friction that when I pull it back, it never even makes it back to the middle. It just stops. Now, if you're wondering why you would have any of this sort of thing, think about a car. Think about a car that has springs that work as shock absorbers to try to smooth out the ride that are connected to every wheel that you have. If those springs aren't working properly, you have an underdamped system, meaning I hit a bump on the road and the spring allows the tire to oscillate up and down around its equilibrium position, which means you go down the road bouncing up and down as you're waiting eventually for that bump to sort of wash away, to die out. That's not good. Critically damped is what you're looking for. You hit a bump, which means that the spring gets stretched or compressed, and then very quickly goes right back to the central location, goes right back to equilibrium without any oscillating back and forth. It's kind of like you don't even feel the bump in that case, which is great. That sounds fantastic. Overdamped is when it would be really, really broken. You can imagine you hit a bump, but then the wheel doesn't go back to where it's supposed to be. You hit a bump, and then the spring is just terribly broken and messed up, and now you've got tire or multiple tires that are out of position, and then your car kind of falls to the ground and everything is terrible. So this is kind of and it's an engineering problem. Different situations. Maybe you want the oscillation to continue as long as possible, so you try to set up the system that's underdamped and try to minimize the amount of friction in the system. Maybe you want something where you're trying to get rid of oscillations as much as possible, like in the car, and you want a critically damped system. So that's some examples of damped oscillations. You can see some diagrams in the book if you want to look into that further. We're not going to do anything else with that. So what if I have a pendulum, starts swinging, and then because of friction, it's underdamped, but slowly but surely its amplitude decreases over time and eventually stops, and then we have to start it up again. Well, what happens to the period doesn't matter. It's based on the length of the string, which is not changing, which means even as the amplitude decreases, the period doesn't change, which is why a pendulum makes a pretty good clock. It doesn't last forever, but it keeps time even as it loses energy because the period stays the same, which is pretty cool. Okay, the period does not change. And there's the answer slide for that. One final slide is, what if instead of losing energy during the oscillations, what if we go the other way around and we put energy in? In other words, we try to either increase the amount of energy in the system or just replace what was lost by doing some positive work on the system. This is what we call driven oscillations. And for this, I want you to imagine pushing a kid on a swing. Clearly, a kid on a swing is a simple pendulum. And all kids enjoy riding or being a simple pendulum. It's fantastic. You go to the playground, get to be a simple pendulum. What's not to like about that? But perhaps the kid wants to be pushed on the swing. Well, you imagine as the kid swings back and forth because of the length of the swing, the length of the pendulum, there is a natural frequency. it takes a certain amount of time for the kid to swing over and back, whether they're swinging just a little bit or swinging a lot. It takes a little bit of time, whatever that may happen to be. So there is a frequency that's natural for this. So, oops, we have that right above. There is a natural frequency of this particular system. Now, as I come along and push, let's say that I'm going to push the kid multiple times. Well, there's going to be a certain space of time in between my pushes, which means I have a pushing frequency. So over here, the frequency of the external force is my pushing frequency. Do I push a lot of times each second, or does it take several seconds in between pushes? Like, how often do I push the kid? Well, clearly, I'd like to push the kid in a way that matches the swinging. If I want the kid to be able to swing higher and higher, I want to increase the amplitude. I need these frequencies to match. You want to push the kid at the same point in the swing every time. They swing back to you, you push them forward. You wait for them to come back, you push them forward. In other words, your pushing frequency matches the frequency of the system, of the pendulum, the natural frequency. If I want to increase the amplitude, the pushing and natural frequency must match. Imagine if they didn't match. Imagine if they're badly off. Imagine if I push like 3 times during each swing of the kid so that my frequency is 3 times as much. Well, then I'm going to push like 1 time at the top, and then I'm going to push again when they're maybe like almost near the other end of the swing, and then I'm going to push again when they're like at the bottom. That's not going to work out so well. The kid's not going to have a lot of fun. You can imagine their swinging has become really erratic, and I'm probably going to kill out the oscillations if I continue to do this, and it's just not going to work at all. So we need these frequencies to match, and if they don't, the oscillations get destroyed or damaged in some way. So pushing and the natural frequency must match. We call this frequency that is in agreement between the two the resonant frequency. And this increase in amplitude we call resonance. And that is about all that I want to talk about in this particular chapter. I think that is about it. And again, these last 2 slides, don't worry about the math or anything. Thank you for watching/listening, and I will see you in class soon.